Like, what does it mean when we integrate this? What are we doing? Finding the, no, it's change if it's whatever, it's the function, that is a derivative, right? But the way we did this from the very beginning is we graph this and we are looking for what? The area under the curve. Yes? Here's 2, and here's 6 over here, right? So that's a bad graph of it, but we're finding the area under the curve. Area of what? How do we do that? How do we find the area under the curve? And what do those things really represent? Infinite what? Riemann sums of what? What are we adding up every time? Little rectangles, right? So the very first rectangle that I drew had a height of what? 0. Okay? So this number right here, these are all of the heights, and these right here, that dx is all of the widths. Yes? The first height is 0. Why? How does that relate to this 2 right here? Huh? You plug in 2 into this x, right? And 2 squared minus 2 times 2 is 0. Right? What is the next one? What happens when I throw in a 3? Let's say that number right there is 3. What is that going to be? You can do that real quickly. It's going to be 3. Yes? Okay? 0, and then this number right here is 3. What about at 4? What is that height? 8. So this height right here is 8. Is that a random height? And then the last height is what? 18, 15. It ain't 15. Okay, what about 6? 6 is the last one, right? What is it? Because I don't know. 36 minus 12 is 24. Okay, now we're good with arithmetic. Okay? So this, when I throw in a 2, the first thing that I do is I get my first height. And I throw in a 6 and I get my last height. Yes? And then how many of these rectangles do I do? What is the width of each of those rectangles?
Almost 0.
Almost 0, right? Almost 0. Are we good? That is the overarching concept. So if they happen to throw a problem like this, if n is a positive integer, so integrals are the exact same thing as an infinite sum, an infinite series, right? And we're making those rectangles in there. So the way that I see it, if you want to just kind of get this in like, just real quickly, n is going towards infinity, and this number right here, so these are all of the heights, and this right here is the width. W-I-D-T-H, whatever. Those are each of the widths, right? Are we good with that? So we need for this, for our integral to match up so that our first width is 2 and our last width is 24 for this problem. So I can make a Riemann sum for this one. I'm just going to make it so I'm going to make the first width 0 and the last width 24, and then whatever in between there, I'm going to hit all those numbers 3, 8, and whatever that next number is. I think you said 15. I don't know, but don't care really. So when we go back here, let's look at this. We want to find an antiderivative because we're doing an infinite number of them, right? So they're all going to be antiderivatives. What is the first? So this is the first height. This is the last height. Okay? So what is the first height that we have in our Riemann sum for this one? If n goes towards infinity, So this represents the height of the first rectangle, the second rectangle, the third, the fourth, the fifth. We have to do that an infinite number of times, right? And then we get that shaded region because we've done so many, it fills up the whole page, right? So the first one is going to be what? 0. Okay? I'm going to go back and I'm going to fix that in just 1 second. 0. Okay? What is our last height going to be?
3.
No.
9.
9. And I'll fix that as well. Because n divided by n is 1. So the last height is 9. Are we good? But more specifically, the first height is 0 squared because we have that squared right there, yes? And our last height is 3 squared. So which one of those are going to give us a first height of 0 and a last height of 9? And I think you might know that, but let's give everybody a chance to get that. Right? Is it A? No. Why not? X is in the denominator. Can you divide by 0? No. So we know that it cannot be A. B, because you can't throw in a 0. Right? And it's not C, because you can't plug in 0 in the bottom. So these are already improper integrals, and we didn't write them correctly. Yes? Because you cannot divide by 0. 1 over 0. Okay? What about D? Does that look good? Is our first height 0? If I throw in 0, is our first height 0? Yes. Is our last height 9? Yes, it is. Okay? So, what about, so D looks good, but this is the first time we've seen it, so we may not be 100% confident in that. So what about this one right here? What about E? Right, because the first one, our first height, is 3 times 0 squared. Because that 3 still, it could be inside of there, right? We just pulled it out. And our last one was 3 times 3 squared, or 27. We wanted our last height to be just 9. So D is the correct answer, okay? D is the correct answer. Are we good? So, now let's do 41. First height, last height. So take a couple seconds and figure that one out. N, so at the very beginning, the first one is just going to be 1, but n still goes towards infinity. N never changes. N is always infinite. Okay? N is always infinite. That'll give us, so the antiderivative, those heights will give us the first and the last. Yes? Okay. So, and there are kind of 2 of them that just work with first and last, but there's one that is more correct. Okay? What do we got? Huh? Yes. How did you know that?
Because like it matches the endpoints, it's also square root.
It's also square root, right? So that's the other thing. We're taking the square root every time, right? The endpoints. That first one is 0. This is basically 0. And this is the square root of 1. That's our first and our last. Okay? So what happens when we throw, so that can't be A. That's 0 and 1. That's 0 and 1, but it's not the square root. So that's why we're eliminating that one. That gives us 1 and 2. Nope. Not a square root. Yep, square root. But that's not, that has a 2 in front and whatever, right? And we have x times the square root of x. Okay? So the other short answer is that I kind of basically ignored this part right here. This is really how we're moving along the x-axis. That's where that takes its place. That is our dx. Okay? That's our dx. And most of the time, that'll be our width of the interval from 0 to 1. It just wasn't for this one. At first, when I saw this, oh, it actually is on this one. Yeah. No, the correct answer is D. I was expecting the width of the interval to be 1 because our numerator was 1. Okay, it just wasn't because this actually, the 3 took care of it inside of here. Okay? So, there is another way we could have written that. So, did we do that one? Yes, we did that one on that page. And that correct answer is B. I don't know why the letter moved and not the dot that time, whatever. Okay, so this is a similar one, but now in this case, we don't have an infinite number of rectangles. We just have a very large amount of rectangles. How many rectangles do we have? 50, right? So you could think of this thing as n. You still could think of that thing as n, and n is going towards infinity. Okay, but maybe not. Whoops. That tells us how many that we have. So this is just a large amount. 50 rectangles is a lot, right? So what are we doing every time? We're square rooting. Oh, so that has square roots in all of the answers. That didn't really help us out. What is our first rectangle? What is our first height? Basically, in this one, pretty close to 0, right? More would just give us smaller numbers, right? 100, 1,000, whatever. It would just get closer and closer to 0. So our first height is 0, and our last height has to be what? 1. And so it's really the same problem, right? If you got the last one, you got this one. Okay? And it's, again, B. And this is from 1997. The other's from 1988. So they took the exact same problem and changed that n being infinity to just 50. Okay? So it's the same answer. Okay? And that's it. So luckily Akshay's not here, so I won't have him come up and do this last one. All right, someone feel confident in that one, to work on that one and come up and do it. It's a little bit different, so there's different ways that these things can look, really. The first two were very similar, 3, 4. Now, one more, this could look a little bit different. The 4 different ways these Riemann sums come. The first height, last height will always kind of help you out, but maybe not for this one. Huh? Yeah, I can try. As big as it can be and still be legible or fit on one screen. What'd you do?
So, basically you can kind of substitute the sigma with the integral.
Beautiful, right? So we're going to, this becomes an antiderivative, okay?
And then you just replace this delta x with dx.
Delta x
Yeah.
becomes dx.
And then from that, you just do the integral.
Of what? What are we integrating? We haven't done anything to integrate.
X to the 1/2 power.
Yes. Okay, good. So we have x to the 1/2 power. But what are the bounds for that, right?
From A to B.
A to B, because that's the interval, right? So we're going from A to B. So all I have to do is just copy that. Okay? And then we just do it, right? Everything is kind of there. Everything is hidden in plain sight for you. When you integrate that and throw in a B, throw in an A, you do get out A. 2/3, right? And we could do that probably in our head. X to the 1/2 becomes 3/2 times 2/3. Throw in a B, throw in an A. Okay? Are we good? That's it.